Good day everyone, and welcome back to my channel, Sir Joe Academy. On this channel, we cover science, that is chemistry, physics, as well as mathematics and English. I want to use this medium to appreciate all of you, my viewers and subscribers. May God Almighty continuously bless you. Our lesson for today is on alternative to practical, and the topic is volumetric analysis, that is titration, which is basically for Waec Neco GC 2026. At the same time, other students preparing for other examinations will find it very useful. Furthermore, the entire students will find the topic, that is the science students, will find the lesson very useful. Having mentioned that our topic or the area of concentration is on volumetric analysis as part of the alternative to practical, I want to let you know that on the day of the exam, that is on examination day, you are not to carry out the experiment practically, but the practicals ought to have been conducted, and the values that were derived will now be used for calculations on the day of examination. Kindly do well to like, share, and subscribe to my channel. I have this question as a guide for all of you preparing for the Waec Neco GC 2026, and other students too will find this question very useful. And at the same time, I would like to advise you and to encourage you to watch one of my previous videos that is titled Introductory Volumetric Analysis, that is titration. So this is the question that I have for you that will be very useful for every one of you. The question says, the following table shows burette reading obtained when 25.00 centimeter cube of a solution of sodium triisocarbonate 4 containing 1.30 gram in 250 centimeter cube of solution was titrated against a solution of hydrochloric acid of an unknown concentration. From this question, try as much as possible to understand that we have the acid. The name of the acid is hydrochloric acid, and the name of the base is sodium triisocarbonate 4. Sodium triisocarbonate 4. The question continues. Now, we are given this table. burette readings, we have column for burette readings, column for rough titration, column for first titration, and column for second titration. Under burette readings, the unit in science, the unit is very, very important. Centimeter cube is the unit that is used here. So under burette readings, we have final burette readings. And after final burette readings, we have initial burette readings, the volume of acid used. So along the horizontal line, now for the final burette readings, under rough titration, we have 21.30 centimeter cube. 21.30 centimeter cube. Now, then the initial value or the initial burette readings under the final burette readings is 0.00 centimeter cube. It means that when acid was filled into burette, when the experiment was being carried out, the acid was filled to the level of 0.00 centimeter cube. Then when the titration was going on, the color changed. The color changed from yellow to pink. The color changed from yellow to pink at 21.30 centimeter cube. Then for the first titration, the initial burette readings is 21.30 centimeter cube, while the final burette readings for first titration is 43.20 centimeter cube. Then for the second titration, the initial burette reading is 0.00 centimeter cube, while the final burette readings is 21.90 centimeter cube. I want you to look at the board very well and then look at the values. Look at the values for the initial burette readings and the final burette readings. I hope you have seen the board very well. Now, there is space. We have a volume of acid used. So which means that this space is to be filled, this space is to be filled, and this space is to be filled. So in order to get the volume of acid used, we have to subtract 0.00 from 21.30 centimeter cube. So which means that volume of acid used here is 21.30 centimeter cube. Then here, the volume of acid used, we have to subtract 21.30 from 43.20 centimeter cube. So here we have 21.70. And here, now for the second titration, the initial burette reading is 0.00 centimeter cube. Then the final burette reading is 21.90 centimeter cube. In order to get the volume of acid used, we have to subtract 0.00 centimeter cube from 21.90 centimeter cube. So we have 21.90 centimeter cube. When you look at this table very well, you will observe that for the first titration and the second titration, the difference between the two values is 0.2. And when you look at the values, when you compare the first titration and second titration with rough titration, the gap is wide. And the rule of, or one of the rules of titration is that the values, the difference in the values of the titrations must not exceed 0.2. It should be plus or minus 0.2. So when you compare between 21.70 and 21.90 centimeter cube, you can now have the difference as 0.2 centimeter cube. And when you look at the volume of acid used under rough titration is 21.30. When you compare this value with the first titration and second titration, the difference is up to 0.4. So which means that we are to use the concordant values, the consistent values. That's for 21.70 and 21.90 centimeter cube for first titration and second titration respectively. Now the questions that follow the table says that's element number 1. We have copy and complete the table. Copy and complete the table. Copy and complete the table. Take note that the equation was supplied. When the equation was supplied, the space was not filled. So it was when I was solving the equation that I solved or included these values as the volume of acid used. So which means that in this case, the table is now complete. Then we move to A Roman figure 2. A Roman figure 2 says calculate the average volume of acid used. Calculate the average volume of acid used. As A Roman figure 2, A Roman figure 2, that's 1A Roman figure 2. Average, that's average volume of acid used is equals to T1 plus T2 divided by 2, where T1 is equals to first titration, which is equals to (21.70 centimeter cube). T2 is equals to second titration, that is the second value for volume of acid used. Now here is 21.90 centimeter cube. So substituting, we have T1 or average volume of acid used is equals to 21.70 plus 21.90 divided by 2. So we now have we have 43.60 centimeter cube divided by 2 which is equals to 21.80 centimeter cube. 21.80 centimeter cube. That's using two decimal places after 21. So we have 21.80 centimeter cube. Look at the way I solve the question very well. So you can now say that average volume of acid used is equals to 21.80 centimeter cube. Now we divide by 2 because we use the first. The rough titration is not considered, it's not used in the calculation. So we make use of the first titration and the second titration. And if we have 3 titrations after rough titration, it means that it has to be divided by 3. In this aspect, we have rough titration, first titration, and second titration. So the average is taken by dividing by 2. Now, we move to question A, 1A Roman figure 3. That is, write a balanced equation for the reaction in the titration. Now, 1A Roman figure 3, balanced equation. That's balanced equation for the reaction. Now, the acid is hydrochloric acid. The formula is HCl, aqueous, reacting with sodium triisocarbonate 4, Na2CO3, aqueous, to produce the salt, and the salt is sodium chloride, NaCl, aqueous, plus water, H2O, liquid, plus carbon 4 oxide. So this is the reaction, that the equation has to be balanced. Now we look at the left hand side, which is for the reactant, and the right hand side, we look at the reactant side, which is the left hand side, and the product side, which is the right hand side. So we have two atoms of hydrogen. So in order to balance hydrogen, we have to write 2 here. So which means that for sodium, we have 2 atoms of sodium, but we have 1 here. So which means that we have to write 2. So there is 2 in this place. So which means that we now look at the mole ratio of acid. The mole ratio of acid is 2, and the mole ratio of base is 1. The mole ratio of acid is 2, then the mole ratio of base is 1. So with this, the equation is balanced. Then we move to, and notice that the indicator for this particular titration is methyl orange. It's methyl orange. As I've said, the indicator is methyl orange. It's methyl orange because the acid is a strong acid. The acid is a strong acid, but the base is a weak base. So we use methyl orange as the indicator for this titration. We move to the next question. The next question says, from the information obtained in A above, calculate the concentration of Na2CO3 in mole per dm³. So we have 1B, then Roman figure, that's 1B, Roman figure 1. That's concentration of Na2CO3, concentration of Na2CO3 in mole per dm³. Now, before the concentration of Na2, sodium triisocarbonate 4, in mole per dm³ is calculated. Firstly, we have to calculate the concentration of Na2CO3 in gram per dm³. In the question, 1.30 gram. In the question, 1.30 gram of Na2CO3, that is sodium triisocarbonate 4, was dissolved in 250 centimeter cube. So which means that if 250 centimeter cube contain 1.30 gram of Na2CO3. Therefore, 1000 centimeter cube will contain 1.30 times 1000 divided by 250. So mathematically, 250 go in 251 and 250 into 1000, we have 4. So we now multiply 4 by 1.30. So we have 5.2 gram per dm³. So which means that concentration in gram per dm³ of Na2CO3 in solution is equals to 5.2 gram per dm³. 5.2 gram per dm³. So with this, So with this, we can proceed by calculating the concentration of Na2CO3 in mole per dm³. Using the formula, using concentration in gram per dm³ is equals to concentration in mole per dm³ times molar mass Now we make concentration in mole per dm³ as subject of the formula. But before that, we calculate the molar mass of Na2CO3 is equals to 23 times 2 plus 12 times 1 plus 16 times 3, which is equals to 46 plus 12 plus 48, which is equals to 106. That's 106. Look up very well. I hope you have seen the calculation very well. That's 46 plus 12 plus 48 is equals to 106. Now, unit is very important in chemistry. Not only in chemistry, physics, and some other subjects, even for those that are taking basic science and tech, because in basic science and technology, we have physics as well as chemistry. So which means that unit is very important. Now, the unit for molar mass is gram per mole. That's gram per mole. So which means the molar mass of Na2CO3 is equals to 106 gram per mole. 106 gram per mole. Now, so we now make concentration in mole per dm³. Concentration in mole per dm³ is equals to concentration in gram per dm³ divided by molar mass. And take note, concentration in gram per dm³ is equals to 5.2, when the molar mass is 106. Molar mass is 106. So we now divide. That's 5.2 divided by 106. So we have is equals to 0.045. 491 mole per dm cube. Mole per dm cube. So this is C. We call this as CB. This is CB. CB. That is concentration in mole per dm cube of the base, and the base is sodium triisocarbonate 4. So you can express it further by saying that this is equals to concentration in mole per dm cube of Na2CO2. Now, having solved B Roman figure 1 as well, we move to concentration of HCl. Now, concentration of HCl. So we move to concentration of HCl. That's B Roman figure 2. B Roman figure 2. That's 1B Roman figure 2. That's concentration of HCl in 1. That's mole per dm cube. Mole per dm cube. Mole per dm cube. So here we using dilution law. Using dilution law. That is CAVA all over CBVB is equals to NA all over NB. Look at the board very well. Dilution law, that's CAVA divided by CBVB equals to NA all over NB. So where CA is equals to concentration in mole, concentration in mole per dm cube, concentration in mole per dm cube of acid, that is HCl, which is to be calculated, is equals to unknown, to be calculated. Then VA is volume of acid. Volume of acid, which is derived from the average volume of acid used, and is equals to 21.80 centimeter cube. Then Na, our Na is mole ratio. Na is equals to mole ratio of acid, which is equals to 1. Mole ratio of acid, which is equals to, no, mole ratio of acid is equals to 2. Mole ratio of acid is equals to 2. From the balance, that's from the balance equation. Mole ratio of acid is equals to 2. Then CB, our CB is concentration in mole per dm cube of base and here the CB, our CB is 0.0491 mole per dm cube. Mole per dm cube. Now, the VB, yes, before I say the value for VB, look at the board. Look at the board very well. Now, VB is equal to 25.00 centimeter cube. Yes, VB, 25.00 centimeter cube is more acceptable than 20.00 centimeter cube. Now, we move to more ratio of base. Meanwhile, the VP is volume of base. Volume of base. So NB is equal to more ratio of base. More ratio of base, which is equal to 1. That is from the balance equation. Okay. So with these values, we now substitute. So substituting or substitute into CAVA divided by CBVB equals to NA all over NB. So we have CA, which is to be calculated. VA is 21.80 divided by CB, which is 0.0491, multiplied by VB, volume of base, which is 25.00, equals to NA, which is more ratio of acid, which is equals to 2. Then NB, that is divided by NB, more ratio of base, which is equals to 1. Now we cross multiply. That is, we use the numerator values to multiply the denominator values. So which means that this implies that CA times 21.80 times 1 is equals to 0.0491 times 25, that's 25.00 times 2 times 2 times 2. So here we have to make CA as subject of the formula. So CA is equals to 0.0491 times 25.00 times 2 divided by 21.80 times 1. So we now have that's 0.0491 times 25.00 times 2 divided by 21.80. So we have 0.1126. 0.1126. So which means that our CA is equals to 0.1126 mole per dm cube. Mole per dm cube. So that is the concentration in mole per dm cube. Concentration in mole per dm cube of HCl, which is equals to concentration in mole per dm cube of hydrochloric acid, which is HCl. Look at the board very well. Look at the board very well. Okay? We move to B, Roman figure 2. That is concentration of HCl in gram per dm cube. Now, concentration of HCl in gram per dm cube. Concentration of HCl in gram per dm cube. This is equals to concentration in mole per dm cube. In mole per dm cube times molar mass. That is molar mass of HCl. Molar mass of HCl. Look at the board very well. Concentration of HCl in gram per dm cube is equal to concentration in mole per dm cube times molar mass of HCl. Now the concentration in mole per dm cube of HCl is, so we substitute now. So conc concentration of HCl in gram per dm cube is equals to 0.1126 times 36.5 times 36.5. I hope you understand how I got 36.5 as the molar mass of HCl. Now, that is molar mass of HCl is equals to 1, that's 1 plus 35.5, which is equals to 36.5 gram per mole. So our concentration, or the concentration of HCl in gram per dm cube is equals to 0.1126 times 36.5, which is equals to 4.1 gram per dm cube. 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 Yes, this is the concentration of HCl in gram per dm cube. It is the same thing as mass concentration. It is the same thing as mass concentration of HCl in gram per dm cube. With this, I believe you have understood how to calculate series of calculations when dealing with the volumetric analysis, that is titration. Take note of this, the following formulas. Concentration in gram per dm cube is equals to concentration in mole per dm cube times molar mass. And concentration in mole per dm cube is equals to concentration in gram per dm cube divided by molar mass. Thanks for watching, and do well to like, share, and subscribe to my channel for more lessons. I wish you best of luck in all your endeavors. God bless you all.